In this video, we're exploring a lot of the key ideas behind chemical reactions. So that begs the question, what is a chemical reaction? And that's how we're going to start. So we know from previous learning that everything, or all matter, is made up of atoms. So chemical reactions are going to involve atoms. So when a chemical reaction takes place, the atoms that are contained in what we start with get rearranged and produce what we end up with. So we start with these reactants and we finish with our products. So a chemical reaction is a process where atoms are rearranged into new substances. That's a sort of very simple, very core definition of what a chemical reaction is. Now, it's important that we're able to recognize when a chemical reaction takes place. So quite often we'll talk about observations. And so, what would you observe? What observations could you make to tell that a chemical reaction had taken place? And when we're talking about observations, they are really anything that we can sense. Now, typically, or most of the time, that's to do with sight. So what can you see that is going to allow you to make a conclusion, or to draw a conclusion that a chemical reaction has taken place? But equally, it could be another sensation. And that's typically how you could tell something was getting warmer or colder. Now, you've got to be very careful, because what you're not really doing is you shouldn't be necessarily holding things or touching things or anything like that when a chemical reaction is taking place, because it could be dangerous to do so. But the principle behind that, how could you tell that there had been some change that you could observe through your senses, is something to consider. So there are four possible signs. So colour change, very visible, very easy to see. Energy transfer. Now, this is going to be the case with every single reaction. So there will always be an energy transfer, but that isn't always something you can see. If the transfer was in the form of light, or you've got an energy transfer in the form of sound, then that is an observation that you can make quite easily. But sometimes it's a change in temperature, and that isn't always abundantly clear. So we'd have to find different ways of checking or seeing whether there was a change in temperature, and one of those ways would be to simply have a thermometer in the midst of the reaction and to see if the temperature of the thermometer changed. Fizzing is a common sign of a chemical reaction. That you'll see there's another word here called effervescence. That simply means the same thing. It just means fizzing. If we see fizzing or effervescence, then what we can conclude is that there is a gas being produced. And if there's a gas being produced, then a chemical reaction is taking place. And then finally, the one that tends to get forgotten is this word here, precipitation. And that's when a solid is formed out of a solution or out of solution. It's not a common word. Most people, if they've heard of the word precipitation, are thinking about rain. If you think about it, rain is something coming out of something else. Here, though, if we were making an observation, how could we tell it was a precipitation or was taking place? Then what we would typically see is our solution going cloudy. So that is normally an indicator, or that is an indicator that we have that there's a precipitation reaction, and so clearly we have evidence that a reaction is taken place. So they're really the four key ways that we can tell that a reaction is taking place. Not every reaction has every single one. In fact, a reaction may only have, or may only be, we can only really tell the energy transfer. Energy transfer will be relevant to all of them, but the colour change is very visible, fizzing is very visible, and precipitation is very visible. Now, one of the things that we need to do, or we need to be wary of, is we need to make sure that we are distinguishing between a physical change and a chemical change. There's quite a lot here on the screen. I'm not going to read it all out. I am just going to highlight a few key bits. What I suggest is that you pause the video and maybe read through it, and then you can ask any questions that you've got. So being careful about a physical change. I mean, it says a change in a way a substance looks or feels, and to be honest, we could probably use that description for a chemical change as well. So how are we making that distinction? Um, you can't always tell necessarily, but you're going to have no new products. So if you know that what's happened is that you've produced no new products, then that's got to be a physical change, and something that is always the case really with a physical change is that you can reverse it. Doesn't mean that that's simple to do, but it's something that you're confident you can do. Now, the most common type of physical change, and this is one where you could recognise this fairly straightforwardly, is a change of state. So whether you've got something going from a solid to a liquid, or vice versa, or whatever. The other type, which often gets sort of ignored or maybe not really thought about, is when two or more substances are simply mixed. Now, it's very important that when we're saying that mixing here, that we're being clear that they remain being a mixture. So obviously, if you've got a chemical reaction, you would mix things together in the first place, but then the chemical reaction would happen. When we're talking about mixing here, we're saying that we are simply mixing two or more things together and they remain as a mixture. There is no chemical reaction that takes place. And normally what that would mean is we could reverse it, we could go backwards, we could unmix our mixture. So when we look at examples, those examples are really ones where there are either changes of state or where there's a mixture being made. So I'm not going to say really much about changes of state, but if there are two here that we would describe as being as mixing, so we've got dissolving salt in water, we could certainly separate those two substances at the end, and then at the bottom we've got stirring sugar into a cup of tea. Admittedly, the tea is already a mixture itself, but it would be possible to separate the sugar back again. Maybe it would require some effort, but anyway, it would be possible to do so. And then when you look at all of those non-examples on the bottom right-hand side, burning a match, making bread from dough, cooking an egg, a nail going rusty, those non-examples are all going to be examples, or all examples of chemical changes. So really, we've got an either-or here. We've either got a physical change or we've got a chemical change. So we've got a similar page now for chemical change. One of the things that you'll note in the definition is that we talk about, or I mention about it being typically very difficult to reverse. So quite often you might see descriptions where they say chemical changes can't be reversed. They can, or most of them can, or many of them can, but it's typically very, very, very difficult. And so it's a useful rule of thumb. Obviously, we've got new products being formed, and we've already talked about the four possible observations we could make that would be signs of a chemical change or a chemical reaction. So we've got the colour change, the fizzing, the precipitation, we've got an energy change. So they would be characteristics or possible characteristics of a chemical reaction. And then when you see the examples, some of those are ones that were non-examples on physical change, but they're all things, where there are new products being formed. And then our non-examples are simply physical change examples. So again, take some time, pause the video, take in what's written here, think about it, and you can ask me any questions that you've got. So I said that every chemical reaction involves an energy transfer, and there are really two directions in which energy can be transferred. It can either be transferred outwards or it can be transferred inwards. There's no other option. And there are two words to describe these transfers. We've got exothermic and we've got endothermic. So one of those is going to refer to when energy is transferred outwards, and one of those is going to refer to when energy is transferred inwards. So we need to sort of get a deeper and better understanding of what those two words, what exactly they mean. So in an exothermic reaction, that X is just like X in exit or X in exoskeleton. These are things that are on the outside. or our ways to the outside. So when we're talking about an exothermic reaction, we're talking about energy being transferred outwards. And the way we describe that is we say that energy is transferred to the surroundings. Okay, so what tends to happen then is that the temperature of the surroundings increases. So we can feel whatever it is getting warmer. So that's a sign of an exothermic reaction. And the majority of reactions are exothermic. So if you think of any combustion reaction, anything where there's a fire, anything where there is burning, then you've got energy exiting, right? We've got energy going outwards, and the surroundings of which we would be part are going to get warmer, or could feel warmer, or the energy is being transferred to us or to the surroundings, so the temperature increases. Endothermic is about when energy is taken in from the surroundings. Now, this description here on the bottom right says the temperature of the surroundings drops. There is another aspect to this that we're going to look at shortly, which means it's not just as straightforward or as simple as saying that if the temperature of the surroundings drops, then it's endothermic. But if you do measure that the temperature of the surroundings drops, therefore the surroundings is getting colder, then that is definitely an endothermic reaction. It's just not the only sign of an endothermic reaction, as we'll see shortly. So this page is just sort of breaking down the two words, just to sort of illustrate what's common about them and what's different about them. I'm not going to read that out. If you want to take time to read it, just pause the video and then, just take it in. So here's a little exercise. Sometimes in test questions, they might give you two temperatures. So reactions taking place, and they give you a starting temperature and they give you a final or end temperature. And then they ask you, sometimes they ask you what the temperature change is. And then quite often they ask you to draw a conclusion as to whether this is an exothermic or endothermic reaction. So we're just going to very quickly do this. So when we're looking at temperature change, we're looking at it. We start with the end temperature or the final temperature, and we subtract the starting temperature. And I'm going to put signs in front of my values, positive or negative, because I want to show very clearly that there is either a temperature increase or a temperature decrease. So when we look at reaction A, our end temperature is 24 and our starting temperature is 12. So our temperature change is 24 minus 12, so that is plus 12. So we have got an increase in temperature. And if we are measuring an increase in temperature, then we are seeing that we are observing a reaction that is exothermic. When we look at the second reaction B, we've got an end temperature of 15 and a starting temperature of 16. So 15 minus 16 is minus 1. And so we have a decrease in temperature, albeit quite a small decrease. But a decrease in temperature tells us that the reaction is endothermic. So what I'd like you to do now is pause the video on a piece of paper or somewhere, do the remaining reactions C to I. Think about what the temperature change is, or work out what the temperature change is using that sort of equation at the top, and then decide whether that reaction taking place is exothermic or endothermic, and then start the video and the answers will appear. So pause it, fill in the missing temperature change and whether it's exothermic or endothermic, and when you continue the video, you'll have the answers. So check your answers and let me know if you had any problems. So energy transfer is a key feature of all chemical reactions, and there's one type of chemical reaction that involves a very clear and definite energy transfer, and that's thermal decomposition. So that can be applied to a variety of chemical reactions, but for those to be thermal decompositions, what's got to happen is we have to supply energy, and we do that by heating, and that's why we have the word thermal. And in doing so, whatever it is that we're heating breaks down into simpler chemical substances. That's the decomposition part. So we've put together these two words, thermal, which means basically heating in this context. Decomposition, which means breaking down into simpler parts. So a thermal decomposition reaction is one in which we heat a substance and it breaks down into simpler substances or simpler chemicals. So the classic example, or a classic example, is the decomposition of calcium carbonate. So you could look for this online. So I'm going to write it as a chemical equation. So I'm just about to do that. So in this reaction, we start with copper carbonate, which is green, and then we heat it. So that's the only reactant that we've got. That's the only substance on the left-hand side. So we heat this copper carbonate, and what happens is that decomposes, that breaks down into two simpler chemical substances, one of which is copper oxide, which is black. So we get the color change that we get a color change, which is a sign of a chemical reaction, and then the other product is carbon dioxide. So we are having to put energy in. This is an endothermic reaction. We are having to heat the copper carbonate. The reaction takes place, the copper carbonate breaks down, it decomposes into two substances. So we've gone from one to two. They must be simpler. It's like breaking apart some Lego bricks that are joined together, and we get as our product copper oxide, which is black, whereas copper carbonate was green. So we have a color change, and we also get a gas produced carbon dioxide. And actually you do sort of see, it's a little odd and a little difficult to describe, but you do see a sort of fizzing within the sort of copper carbonate / copper oxide powder. So this page is just sort of repeating, in a sense, my description of thermal decomposition. So just pause the video and take it in, and then start again. Okay, so we started with what a chemical reaction was. It's a process in which where atoms are rearranged into new substances. We then looked at the signs of a chemical reaction. There were 4 particular signs we looked at. We then looked at one of those a little bit more closely, which was energy transfer. So we've been putting together some of the core principles behind a chemical reaction. But of course, we need to start looking at specific chemical reactions. And one of the things that we need to be confident at or comfortable with doing is naming compounds, or vice versa, sort of understanding the names of compounds. So we're just going to look at the rules for naming compounds. So when you've just got a metal and a non-metal in a compound, and the way that you would tell whether that was the case or not is you'd look at the name, or you'd look at the chemical formula, and you would use your periodic table. So you do need to remember in your periodic table whereabouts the metals are on the periodic table, which is basically the center and left, and where the non-metals are, which is basically the top right. But you need to appreciate exactly where that division it lies. If you have a metal and a non-metal, then the metal will always be the first part of the compound's name, and then the non-metal will have its ending changed to "ide." Right. So if you see a compound with "ide" at the end of its name, then you know that the elements present in that compound are the metal at the beginning of the word, or the substance at the beginning of the name, and then you've just got to change the substance that's got "ide" at the end. You've got to change it into its normal sort of elemental name. So let's look at some concrete examples here. So in our first one, we've got iron and sulfur. So if they are in a compound together and they are the only 2 elements, then our compound is iron, because the metal always comes first, and then we're going to change the sulfur to sulfide. And I've just used an F instead of a pH. It doesn't really matter. I really should have checked this before I did it. The convention nowadays is to use an F instead of a pH for sulfur, but it really doesn't matter. So don't get too caught up in that. Magnesium and nitrogen. So nitrogen is not always an obvious one in terms of how exactly you change the ending to "ide." So that's why it's a good example here. So our compound is going to be magnesium first, because the metal is always first, and then it's going to be nitride. So that wasn't necessarily completely obvious. That's why it makes a good example. The next one, we've got the non-metal missing, but we know that the compound is called sodium chloride. We know the ide at the end of chloride is a change from what it would have been in the original element. As you do more and more chemistry, you will recognise elements more and more more quickly or more easily, and so this is chlorine. We've got a metal and then oxygen to form tin oxide. Well, the metal is going to be exactly as the start of the compound name is, so that's going to be tin. And then we've just got aluminium bromide. The compound, we've got to work out what the metal and non-metal are. So obviously aluminium for the metal. And then for the non-metal, again, we know that ide isn't how it ends on the periodic table. Again, as you become more and more familiar, you're going to spot these things, but you're going to look for the brome on your periodic table, and you will eventually find that it's bromine. That looks like it should be pronounced bromine, but it's actually pronounced bromine, just like chlorine is pronounced like that as well. Sometimes compounds contain more than two types of atom. So we've got an example there, CuSO4. So there we got copper and sulfur and oxygen. When that's the case, if you have the third of the elements or third of the types of the third type of atom is oxygen, then what you do is you change the ending to 8. So on the previous slide we were looking at changing the ending to ide. In this one we're looking at changing the ending to 8, and that 8 means with oxygen. So if you ever see the name of something with the name of a compound and it's got 8 at the end of it, then that means there is oxygen present. So if we look at the examples we've got here, my three elements here, or three types of atom, are copper, sulfur, and oxygen. And so the compound that would be formed there would be copper, because it's always the metal first, and then sulfur, and then instead of ide, which it would have been if it was just copper and sulfur, it's 8. So it's copper sulfate. If we look at the next one, we've got sodium, nitrogen, and oxygen. So again, sodium, there's the metal, so that goes first. And then if it had been just sodium and nitrogen, we would have said sodium nitride. But because we've got oxygen as well, we're going to have it as nitrate. And then the final example, we've given the compound's name, which is calcium carbonate. So the calcium tells us straight away what the metal is. So it's calcium. And then the second part of the name is carbonate. So the 8 tells us it's oxygen. It's the third type of atom, and then it's carbon. So carbonate. Whenever you have compounds that contain just carbon and oxygen, or just sulfur and oxygen, the number of oxygens can vary, i.e. there's more than one possible compound when carbon is bonded to oxygen, or when sulfur is bonded to oxygen. And so we need to make it clear which of those compounds it is we're talking about. And so we do that by making it clear in the name how many oxygens there actually are. So if there was only one oxygen, we would use the word, or we'd use the prefix mono. If there were 2 oxygens, it would be di. If it was 3 oxygens, it would be tri. And we would have those prefixes with the oxide. So we would have monoxide, dioxide, trioxide. And that would be in the second part of the name. So if we look at our example here, we've got carbon and oxygen, and it's saying we've only got one oxygen. So our compound is going to be carbon and then monoxide. So the monoxide is telling us it's carbon bonded with just a single oxygen. When we look at the next one, we've got carbon and 2 oxygens. So we make that clear by calling the compound carbon dioxide. When we look at sulfur and oxygen, and we've got sulfur dioxide as the final name, that tells us we must have had 2 oxygens. And then when we look at sulfur and oxygen, we have 3 oxygens, so that's got to be sulfur trioxide. So this is only relevant at the moment when you've got oxygen and carbon only in our different compounds, or sulfur and oxygen only. So the periodic table tells us how to name elements, and we now know how to name compounds. So we can put this all together, and one of the things that we can now do is to write reactions, or to show reactions in terms of word equations. So at the core, at the heart of writing these word equations is the arrow. That is the action of the reaction, as it were. So we have reactants that we start with, and they are on the left-hand side of the arrow. And then when those atoms are rearranged and the reaction takes place to make the products, we have the products on the right-hand side. So the arrow is sometimes, if I was reading this out, if I was reading this equation that's written at the centre there, I would say the reactants go to and then products, or react to form and then products. So our reactants are whatever we start with, our products are whatever we make. So now what we're going to do is we're going to convert some sentences that describe reactions or describe a reaction into a reaction equation, into a word equation. So it says magnesium burns in oxygen to make magnesium oxide. And so what the to make is our arrow. So the magnesium and oxygen are our reactants, and the magnesium oxide is our product. So if we're going to write that, it's our magnesium plus oxygen, and they make magnesium oxide. Hydrogen burns in oxygen to make water. So to make is our arrow. So we have hydrogen as one of our reactants, oxygen as the other, and they together react to form water. Lead nitrate and potassium iodide react to form. So our arrow is the react to form, lead iodide and potassium nitrate. So lead nitrate is one of our reactants. The potassium iodide is the second. They react together to form lead iodide and potassium nitrate. Oops, sorry. And potassium nitrate. Sorry for not making that all on one line. Hydrochloric acid reacts with calcium carbonate to make, so that's where our arrow is. So hydrochloric acid is one of our reactants. Calcium carbonate is the second. Oh dear, I'm not going to have left enough space. They react to form calcium chloride plus water plus carbon dioxide. Again, apologies for not making that all fit on one line. So let's consider some of the consequences of a chemical reaction, and something for us to think about are the physical properties of the substances. So physical properties are particular characteristics, so we could be talking about their colour, we could be talking about whether they conduct or not, or to what extent they conduct. We could be talking about their melting or boiling point. We could be talking about how strong they are, their strength, and we could be talking about whether they're magnetic or not. And they're just some of the characteristics we could be talking about. So if we think think about that in a specific reaction, we could be reacting sodium and chlorine together to make sodium chloride. So you can see them right in front of you there. So it's maybe not super clear in image A, but that sodium is a metal. It's being stored under oil actually because it's very reactive. Chlorine there is a gas, and then sodium chloride is there is a white solid. So there are differences clearly in their melting or boiling points. The fact that chlorine as a gas tells us that its melting and boiling points are much lower than the sodium and the sodium chloride because they are still solid, and we're talking about them being here present at room temperature. We can see colour, so obviously sodium looks like a metal. It's got that shiny appearance, that sort of luster. Chlorine as a sort of a green gas, although maybe that doesn't look terribly green, but it's a green gas, and its name comes from the Greek word for green. And then the sodium chloride, as we said, is a white solid. Now, sodium is extremely reactive. That's why it's being kept under oil in this picture. Chlorine is extremely toxic and was used as a chemical weapon in the First World War. And sodium chloride is something that we may add to our food, but which is something also present in lots of our food. So very different properties. We've taken two very reactive substances, one of which is extremely toxic, and we have combined them, chemically combined them, to produce a compound that, well, as long as you don't take too much of it, is something that actually we, to a certain extent, need in our diet. So this page just sort of summarizes that, so I won't repeat it, I'll just let you read it, so maybe pause the video. So what we're to take away from this is that whatever we're making in a reaction, the properties of that product, and in this case the properties of the compound, because we formed it from two elements, those properties have nothing in common with the properties of the elements that made it up. So there are no similarities in the properties of sodium chloride here with the properties of the sodium metal and chlorine gas. A popular reaction is between iron and sulfur. So we can see that iron, well, we can't necessarily see that it's a metal, but it is a metal. I'm sure you're familiar with that. Here it's presented as a sort of in a sort of powder form. Iron is one of only three elements that are magnetic. So one of the properties of iron is that it is magnetic. Sulfur is not magnetic. We can see also that it's a very sort of vibrant yellow, has a very strong and bold colour. So when those two elements react together, they form something called iron sulfide. You can clearly, well, hopefully you can clearly see that just from a visual appearance, iron sulfide is quite different to the two elements that formed it. One of the other things to say is that one of our elements was magnetic, iron, but our product, our compound, iron sulfide, is not magnetic. It has quite different properties to the elements that formed it. It has a different melting point. Sulfur has quite a low melting point, maybe around 100 plus degrees Celsius. We've got a substance with very different properties than the two reactants that we used to form it. If we had a mixture of iron and sulfur, so we'd simply mix them, we hadn't actually we hadn't kick-started the reaction, then it would be possible to separate that mixture, to separate the iron from the sulfur by using the iron's magnetic properties. We could do that. So that also shows how that was the mixture. Mixing the two together was simply a physical change. And what you actually need to do is you need to provide some energy to get the reaction to start. That's when the chemical change takes place. We can reverse the physical change, the simple mixing, but we can't reverse the chemical reaction. So we come now to conservation of mass, which lies at the heart of chemical reactions. So you might have heard of conservation elsewhere in science. So when you did energy, hopefully you heard about the conservation of energy, and what that said was that energy could not be created or destroyed. It could only be transferred from one store to another. Well, the conservation of mass is similar in that atoms cannot be created or destroyed, but they can be rearranged into new substances. So what that means is if I had 56 grams of iron and reacted it with 32 grams of sulfur, I would make 88 grams of iron sulfide. So our mass is conserved. So the total mass of our reactants must equal the total mass of our products. To just sort of show that a little more clearly, everything is made up of atoms, and all that happens during a chemical reaction is that these atoms get rearranged, they get put into a new pattern, but they are never created or destroyed. That's extremely important. So as a consequence, and that's hopefully what this bar sort of diagram is showing, is that the total mass of the reactants is the same as the total mass of the products. This image is just really here to show you that rearrangement, but to show you that the number of atoms hasn't changed. Now, sometimes we can observe reactions in which it appears that mass isn't conserved. So this reaction here, which you could look up on YouTube, so if we react marble chips, which is basically calcium carbonate with hydrochloric acid, and we measure the total mass during the reaction, one of the things that we would see is that the mass would appear to decrease. So it would seem that the conservation of mass wasn't being obeyed. So we have to understand that, we have to explain it. Now the reason for this apparent contradiction is that about what is it that we are actually measuring. And so all of our reactants will be in our conical flask, and our conical flask will be on the mass balance. So when we begin, the calcium carbonate and the hydrochloric acid, their total mass is being measured. As the reaction takes place, one of the products is a gas. If the conical flask is open at the top, if it's not sealed, then what will happen is that carbon dioxide will escape the conical flask. So as the reaction is taking place, one of the products is leaving the conical flask and therefore is not being measured anymore. So it appears that we are decreasing in mass, but actually what's changing is what we're actually measuring the mass of. So at the very beginning, in the conical flask on the mass balance, we have the calcium carbonate and the hydrochloric acid. If the reaction finishes, all that's in our conical flask is the calcium chloride we've made and the water, but not the carbon dioxide. So we're not measuring all of the products. So it appears as though the mass has decreased, but in fact all that's happened is that some of the mass we should be measuring has left the conical flask and is no longer being measured. The conservation of mass, as I hope these bar diagrams show, is still being met. Mass is still conserved. Equally, there are some reactions in which the mass appears to increase. So, and again, it appears to contradict the principle of the conservation of mass. So if we take this example, which is burning iron wool, if you have your iron wool on a mass balance and then you allow it to burn, what will happen is the mass being recorded by the mass balance will increase. So again, we've got to explain, well, how can we explain this if it is the case that mass is always conserved? And again, it's about what's actually being measured on the balance, what masses are actually being measured. So when it starts, this is a similar example, like the other one was iron wool, but we've got an example here with magnesium. It's the same principle. The magnesium, when it reacts, is actually reacting with oxygen in the air. Now on the mass balance, it's only the magnesium that's being measured, not the oxygen that will then react with the magnesium. However, once the reaction takes place and we make the magnesium oxide, what's being measured by the mass balance is the mass of all the magnesium atoms and all of the oxygen atoms that have joined with those magnesium atoms. So those oxygen atoms weren't being measured initially on the mass balance, but are being measured afterwards. So it appears as though the mass has increased, but actually we still have conservation of mass. It's just really about what we were measuring at what point, at what time. So sometimes questions will rely on our understanding of the conservation of mass to have us work out how much of a reactant or a product was either used or formed. So this is just a quite simple and straightforward example. We've got 30 grams of magnesium oxide being formed. We started with 18 grams of magnesium, so how much oxygen reacted? Well, one of the things that we know is that the total mass of the reactants must equal the total mass of the products. So 18 plus whatever our question mark must equal 30. So our question mark must equal 30 minus 18, which equals 12. So the mass of our oxygen on the left-hand side is 12 grams. So if you ever have a test question in which they ask you, in which they give you some masses and then they ask you for the mass of something that they haven't given you, and it's referring to a reaction, just remember conservation of mass and think about what are your reactants, what are your products, what are the masses they've given you, which is the one that you're trying to find out. And remember that the total mass of the reactants must equal the total mass of the products. So now we come to balancing equations. So this is the end of the topic. This is the culmination, I guess, of the work we've been doing on chemical reactions. Now, before we can really plow into balancing equations, we've got to make sure that we completely understand chemical formulae. That we've got to understand what the formula like CH4, what it actually tells us in terms of how many of each type of atom are there. So the first thing to sort of stress is that the subscript numbers, so they're the small numbers, they always refer to the element that they come after. So that 4 only refers to hydrogen in this CH4. So what that CH4 means is that we have 1 carbon atom and we have 4 hydrogen atoms. I want you to pause the video and have a think about each of those formulae and write how many of each atom you think there are, and then compare your answers with mine. So pause the video now. So in H2O, the little 2 refers to how many hydrogens there are. So there are 2 hydrogens. There is no number after the oxygen, so there is 1 oxygen. In NH3, there's no number after nitrogen, so it's 1 times nitrogen, and there is a little 3 after hydrogen, so there are 3 hydrogens. CO2, no number after the carbon, so 1 carbon, 2 after the oxygen, so 2 oxygens. C2H6, so there is a 2 after the carbon, and there is a 6 after the hydrogen. And then C2H6O, there's a 2 after the carbon, there is a 6 after the hydrogen, and there is no number after the oxygen, so there's 1 oxygen. This time we're looking at similar formulae, same or similar formulae, but the one difference that we've got is we've got a number in front of the formulae. So a way of thinking about that is that it's like saying this. So it's 3 of what's inside the bracket, so it's 3 of the formulae. So when we did H2O, we knew there were 2 hydrogens and 1 oxygen. So if we have a big 3 outside, then that means we have 3 times what we said was inside the brackets. So we have got 6 hydrogens because it's 3 times 2. And we have got 3 oxygens because it's 3 times 1. There's no number after the O, so that means its value is 1. If we look at NH3, we're saying 2 of whatever's in that formula NH3. So we have got 2 times 1 nitrogens, so 2 nitrogens. And we've got 2 times 3 hydrogens, so 6 hydrogens. Then when it comes to CO2, we have got a 4 in front of it, and so we're saying 4 CO2s. So you can probably pause the video actually and try and finish the rest of these, but I'll just carry on. So pause the video. So we've got 4 carbons, and we have got 2 times 4 oxygens, so that is 8 oxygens. And then when we look at C6H12O6, so it's 2, and then the formula. So we must have 12 carbons, 24 hydrogens, and 12 oxygens. So you can look this reaction up on online. So hydrogen balloon reaction. Basically, it's the combustion of a balloon containing hydrogen. When that reaction takes place, water's formed. So if we were writing our word equation, it would be hydrogen plus oxygen goes to water. And we can now think about what the chemical formulae are for each of those substances. So for hydrogen, it's H2, oxygen, it's O2, and water, it's H2O. So here it is represented. Now, if we think back to what we were doing a little earlier, which was the conservation of mass, we said atoms cannot be created or destroyed, only rearranged. And hopefully, I'm hoping you, when you look at this equation at the top there, you see that there's a problem. If we count how many hydrogens we have on the left, we have 2, and on the right we have 2. But if we look at the oxygens, we've got 2 on the left and only 1 on the right, and that can't be correct because of the law of conservation of mass. Remember, atoms are not created or destroyed, they only rearranged. So we must have the same number of each atom on both sides. So what I'm going to ask you to do is I'm going to ask you to watch a separate video. So I'll have the link in the description, or I've already linked it to your classroom, but I want you to watch balancing equations, my video on balancing equations using the bubble method. This leads you through a sort of a step-by-step method, or gives you a step-by-step method for being able to balance equations. One of the key things, though, is that you are comfortable, completely comfortable with understanding what a chemical formula tells you, which was what we were just doing a couple of minutes ago. So the next few slides I'm really only going to show. I'm not going to really say anything. I'm not going to do the balancing equations here because I have done that on a separate video. So really, to continue from here, you need to watch that balancing equations using the bubble method video, or if you've already seen it or you feel comfortable with balancing equations, then you can use the next few slides that I'm going to show as a practice. And if you get everything right, or everything's going great, then brilliant. And if it's not going great, then I suggest you either watch again the video, or watch it for the first time. Okay, so this assumes that you are comfortable with balancing equations, so that you either feel very confident from what you've done in class, or you've watched the video that I was just mentioning on the previous slide. So I'm just going to let you, I suggest you pause the video, you try and work out what the correct balance equations are, and then I'm going to show you the answers. So please pause the video. So here are the answers. Okay, and again, just pause the video and you can double check yours. If you've got one wrong and all the rest are right, then you've probably just made a little silly mistake. Think about why or how you made that mistake. If you've got lots of them wrong, then you want to either make sure you've watched the video on the bubble method, and if you have already done that, then get in touch with me and we'll sort out how we can try and fix it. And so to finish, here's a list of equations for you to balance. I'd like you to just go ahead and do those, do them on a bit of paper. I'm not going to talk you through, I'm just going to show you the answers in a minute. So I want you to pause the video, have a go at them, and then check your answers from the next slide. And these are the answers. If you've got 1, 2 wrong, then just think about why or how that happened, but otherwise, fantastic, well done. If you've got a lot wrong, again, make sure that you have watched the bubble method video, maybe watch it again. If there's something you're not getting or something you don't understand, then please just get in touch with me and we'll try and sort it out. But that finishes the whole chemical reactions topic. So I hope things have been clear, but if you have any queries, please let me know.